Okay, for what we have in numbers 3 through 6, it says to evaluate each of the logarithmic expressions and equations. If the result is not an integer or terminating decimal, then round to the nearest 3 places. All right, so for what we have in this set, okay, so we have a base 5 logarithm of 26, and we can use what is referred to as the change of base formula. And again, for the change of base formula, okay, if I have so I have something like the base A logarithm, the attachment m, that's going to be equal to the base B logarithm of the attachment m all over the base B logarithm of the original exponential base, where we had the base B logarithm of A. And for what you have in your calculator, your base B logarithm could be either a natural or base 10 logarithm. So we can say that we have the natural logarithm of m over the natural logarithm of A, or you could say that we have the log that is in your calculator. That will make reference to a base 10 logarithm. So you have that of m all over that of A. So we have for the base 5 logarithm of 26, and we'll just use the natural logarithm on this one. So we have A represented by 5, m represented by 26. And so we can say we have the natural logarithm of 26 over the natural logarithm of 5. And you have to hit or keystroke ln twice. You cannot say it like the natural logarithm of 26/5. So we have here for the natural logarithm of 26 divided by the natural logarithm of 5. And we have to the nearest 2 decimal places. This will be about a 2.024. Now, for the base 7 logarithm of 19/13, and we'll just go with the base 10 logarithm on this one. So we'll just have the log of 19/13 all over log. And just taking what we have now, so you have base 10 logarithm of 19/13 divided by the base 10 logarithm of 7. So this will come out to a 0.195. Now for the base 3 logarithm of 38/3, and you can use log again, or you can just go with the natural logarithm. And here we're going to have the natural logarithm of 38/3 all over the natural logarithm of 3. All right, so you have m represented by 38/3 and A represented by 3. Okay, so in taking what we have for the expression, and we have to the nearest 3 decimal places, this will be about a 2.311. All right, now for number 6, now we have sums and differences of logarithms in the same base. And when we look at gathering expressions in the same logarithmic base into a single term, okay, we're going to have addition is going to imply multiplication of the attachments, whereas subtraction is going to imply division. Okay, and what I mean by this, okay, we have with the first 2 terms, okay, we have added together, but in the attachment, we're going to have 19 and 25 are going to multiply each other, and with the following, or that which will follow with the subtraction, the base 54 logarithm of 10, we have 10 is going to be divided into what we have for 19 times 25, and 19 times 25 divided by 10. Okay, this will come out to base 54 logarithm of 47.5. And I can follow through utilizing the change of base formula. And we'll just go with the base 10 logarithm on this one. So you have a base 10 logarithm of 47.5 divided by the base 10 logarithm of 54. And so for what we will have taken to the nearest 3 decimal places, okay, and we have approximately 0.968. Okay, for numbers 7 through 9, okay, it says to write each expression as a sum and or difference of logarithms, and to express powers as coefficient factors. Now, for what we have in the case of number 7, okay, there's some properties to look at. Now, if you have a match between the exponential and the logarithmic bases, like if you have a base A logarithm of a to the r, this would just go to the power. Now, in the case of what we have for sums and differences of logarithms, okay, and these will work in both directions. We have multiplication of the attachment, where we have the base A logarithm of m times n. The expanded form will translate out to the base A logarithm of m plus the base A logarithm of n. And here we have with our other property, okay, division will imply subtraction, where the base A logarithm of m over n is going to be equal to the base A logarithm of m minus the base A logarithm of n. So anything that is at the top will refer to a positive logarithmic term, and anything that is at the bottom is going to refer to a negative logarithmic term in the same base. Now, for what we have in the case of number 7, okay, we have a mix of radicals, and if I rewrite the radical portions in terms of non-integer exponents, okay, so we have a base 3 logarithm of x squared, and we have times the cubic root of y to the 5th, so this will translate out to y to the 5/3. And for the 6th root of z, okay, we have, this will become the base z raised to the 1/6 degree, and we have all over 9 times the 4th root of b, and the 4th root of b becomes b raised to the 1/4. And if I start to write in expanded mode, okay, now anything that is at the top will be positive, anything that is at the bottom will become negative. So you have the base 3 logarithm of x squared. And we say we have plus the base 3 logarithm of y to the 5/3. And we have plus the base 3 logarithm of z to the 1/6. Now for what we have in the denominator, we have minus the base 3 logarithm of 9. And we have minus the base 3 logarithm of b to the 1/4. Now we got our exponents, okay, to which we're to write as coefficients. But now let me mention something about the number 9. Okay, we're looking at 9, okay, and 9 is not only a multiple of 3, but it is also an integer power of 3. So the base 3 logarithm of 9 is going to become, on the basis of the base A logarithm of a to the r equal to r. We have the base 3 logarithm of 3 to the 2nd, and you can look at a represented by 3 and r represented by 2. So this particular term, this will go to 2, which is going to be subtracted. And we have for the final answer that we have in problem number 7, we have 2 times, okay, the base 3 logarithm of x, and we have plus 5/3 of the base 3 logarithm of y, and we have plus 1/6 of the base 3 logarithm of z, okay, and again we have minus 2, and we have minus 1/4 of the base 3 logarithm of b. And that will be the final answer in this one. All right, for number 8, we have the base 5 logarithm of 7x squared y cubed all over w to the 4th times the square root of z squared plus 5. And for this one, if I go ahead and write the square root as a non-integer exponent, where we're just going to have the quantity of z squared plus 5 raised to the 1/2. Now, looking at expanding, so we're going to have the base 5 logarithm of 7 plus the base 5 logarithm of x squared, and we have plus the base 5 logarithm of y to the 3rd. And then with the rest of the terms we have in the denominator, so we have minus the base 5 logarithm of w to the 4th, and we have minus the base 5 logarithm of z squared plus 5 quantity to the 1/2. All right, and now the first term is already in reduced form, and 7 is neither a multiple nor an integer power of 5. So we had the base 5 logarithm of 7, and then where we have exponents, we're going to write as coefficients. So the second term, we have 2 times the base 5 logarithm of x. Then we have followed by 3 times the base 5 logarithm of y. We have minus 4 times the base 5 logarithm of w. And we have minus 1/2 the base 5 logarithm of the quantity of z squared plus 5. Okay, for number 9, we have log, which would be in reference to a base 10 logarithm. And here we have that of 10 times u to the 3/4 times x to the 5th times the cubic root of z to the 4th minus 13. And we have all over the square of the quantity of w plus 1. And we have times y to the 2/3. Now, working with what we have here. Now, for the cubic root of z to the 4th minus 13, writing as a non-integer exponent. Okay, we have the quantity of z to the 4th minus 13 raised to the 1/3. Okay, so looking at expanding. Okay, so we have at the top, okay, we have the base 10 logarithm of 10. And then we just mentioned, okay, so you have the base 10 logarithm of 10. You read that as the base 10 logarithm of 10 to the 1st. Okay, so we can say at least for this particular term, okay, that is going to be equal to 1. Okay, and then we have next in line, we have plus the base 10 logarithm of u to the 3/4. And we have plus the base 10 logarithm of x to the 5th. And we have plus the base 10 logarithm of z to the 4th minus 13 quantity to the 1/3. And we have in the follow through, okay, we have minus the base 10 logarithm of the square of w plus 1. And we have minus the base 10 logarithm of y to the 2/3. Okay, and so for what we have this time, okay, so again, the first term, base 10 logarithm of 10, that's going to go to 1. And for the rest of the terms, we're going to write the exponents as coefficients. So we have 1 plus 3/4 of the base 10 logarithm of u. And we have plus 5 times, okay, the base 10 logarithm of x. And we have plus 1/3 of the base 10 logarithm of the quantity of z to the 4th minus 13. And for the rest of the terms, I'm going to have minus 2 times, okay, the base 10 logarithm of the quantity of w plus 1. And I have minus 2/3 of the base 10 logarithm of y. And that will be the result in this case.